So, I will be talking about Gaussian mixture models and the expectation maximization algorithm. So, the plan is to start with introducing Gaussian mixture models and then talk about mainly how we estimate parameters for a Gaussian mixture model, and then through that introduce what expectation maximization is, because that is the iterative algorithmic framework that we will be using for parameter estimation. That is in general, and then we will come back to Gaussian mixture models and see how EM can be used for Gaussian mixture models, and then talk a little bit about why EM is a nice way to talk a little bit about theoretical properties of EM and why it is interesting. So, mixture models, as the name suggests, they are a mixture of different they are a mixture of models. Like formally they are linear combinations of simpler, not always simpler, but linear combinations of distributions. So, they typically have a form like this. So the density of a mixture model is a linear combination of other densities P, and different mixture models will have different forms for the probability distribution here, right. Pi k, so let me write this down, so because we will see this quite often. So, the density is given by a linear combination of different probability densities, and here we have k components, and each of these components have a mixture weight. So, this pi k is called a mixture weight or a mixing coefficient, right. So, this probability here it can assume different parametric forms. The most common is the Gaussian. So, when this takes when this follows a Gaussian, this is called a Gaussian mixture model, right, and this is one of the most commonly used mixture model in a lot of different domains, in bioinformatics, in speech processing. You will see this everywhere. One of the reasons why it is used is because it is mathematically tractable, but there are other nice properties too. So, I guess you all know what a Gaussian is, but let me write it down anyway, so that, because we will use this very often in the coming few slides. Right. So, this is the form of a Gaussian. I am assuming you all know this, but let us keep it. So, each Gaussian, each component here is a Gaussian, and each of these Gaussians have its own parameters, the mean parameter and the covariance parameter, right. And for this to be a valid density, we need the pi k's to be between 0 and 1, and also the sum of all the pi k's to be exactly equal to 1. We can show this mathematically, okay. So, why do we need these mixtures? Why do we need these superpositions of densities? So, here is an example from Bishop's book. It is a very well known data set, old faithful data set. On the left, so we have plotted the data set in green points, it is a 2-dimensional data set, and when we try to fit a Gaussian, this is what you get, right, when you try to fit a Gaussian here. Now, visually it clearly looks not okay, because the Gaussian is most dense around the mean, but when you see the data, it does not look like the data is most dense around the mean, right. But if we use, instead of a single Gaussian, 2 different Gaussians and try to fit a mixture of 2 Gaussians to this data, it looks somewhat okay, the data is dense here and data is dense here, and it looks like this a mixture of two Gaussians would be a good fit for this data. So let me show you some more examples. Before I go into this, let me show you some more examples. Right. So this is just some R code to generate to sample data from a Gaussian mixture, and what I am going to do is just sample and then plot the data. Right. As you can see, every time I sample from a Gaussian mixture, it's basically here I am setting the number of components to 3. So every time it is sampling from 3 different Gaussians, and whenever you see this, what you typically see is this clustered kind of data. So you see 3 clusters. If I change this to 5 or 6, you will start seeing more clusters here, not necessarily well separated like this, they may be overlapping as well. You see. So whenever you see such clustered kind of structure in the data, the first thing that comes to mind is that that comes to mind when you try to model such data is to try to use Gaussian mixtures, because Gaussian mixtures can nicely fit such clustered data. So this is another figure from the same book, illustration of 3 different Gaussians. You see, as I was saying, these Gaussians need not always be well separated. In this case, these Gaussians, because the mean and variance that are chosen, they are overlapping, right. And here you know that somebody is telling you that there are 3 different Gaussians, but when you look at the data and try to plot the density, like the fitted density, it looks something like this, right, and this is the surface plot of the distribution. Another thing that you should observe here is that this was generated from a 3 component Gaussian mixture with weights 0.5, 0.3 and 0.2, right, which means that the red Gaussian here is contributing most of the mass, and that is again observed here when you plot the density. So this mean here is the probability here is the highest, and then a bit lower for the green Gaussian and the lowest for the blue Gaussian, right. Right. Let me show you some more examples of these densities. So again I generated from 6 different components. Let me reduce the number of components here to 3. There you see, this is an example that I wanted. So here there are 3 components, but the 2 components are highly overlapping. So if you see how it was generated by one Gaussian here, a second Gaussian here, and a third Gaussian here. But when you look at the data, you don't know how it was generated. It looks like this. So sometimes it may not be apparent that there are exactly 3 different components. And when you plot the fitted density, you typically see a density curve like this, which has multiple modes, right. Now this is a fitted density for a 3 component Gaussian. You see, it does not necessarily have exactly 3 modes. So it depends on the sample that you have. So let us see a few more density plots. You see, this is the data that I generated, and this is the fitted density, which has 4 modes. Let us run it again. This is exactly 3 modes for this data. This is very well separated, the 3 clusters. Okay. So, you might have already understood this by now, at least intuitively. We can formulate this as a generative model as well, right? And the generative model would be to select a component, right? Once you select a component, you know you have selected the Gaussian corresponding to that component, and you know the parameters of that Gaussian, and then you sample data from that Gaussian. So that would be a generative model for a Gaussian mixture, right? To make it more formal, so let us take Zn to be a categorical random variable, right, with the probability of Zn equal to k being exactly equal to this pi k, right. So, it is a categorical random variable which takes values from 1 to k, and now suppose that the probability of the data xn given Zn equal to k. So, what is the probability of, which is just this, the probability of xn given that you know the parameters for that particular component. I express it as probability of xn given theta k represents the parameters. So, the marginal distribution, you can express it as probability of Zn equal to k, you select the component, and then the probability of xn given Zn equal to k, the probability of xn coming from exactly that component. By what we have assumed, the first probability is just pi k, and the second probability is probability of xn given theta k. Right. So, this is an equivalent generative formula with an explicit latent variable Zn, and we can represent this graphically. The shaded circle here is the observed data. This is the latent variable. The latent variable is governed by the parameter pi, and xn is generated, once you know the latent variable, it is generated by known parameters corresponding to that latent variable. So, if you have to generate data from such a model, you first sample Zn from the categorical distribution, which is just, so the categorical distribution is a special form of multinomial distribution with parameter 1, and so that once you sample Zn, you get the kth component with parameters theta k, and then you sample xn from that probability distribution. So, in our case this is Gaussian, but it need not be Gaussian, it could be exponential, it could be any complicated probability distribution. Right. Right. So, is it any questions? Please ask me if there are any questions.
Excuse, could you go to the previous slide again? Could you explain the third?
So, the probability of xn, so we are just getting the, so we are assuming that there is a joint distribution, and the marginal distribution can be written down like this. You, for each of the k components, you take the probability of Zn being equal to k, and then the probability of xn being generated from that component. So, this is exactly what the graphical model represents, right. If you write down the probability distribution represented by this graphical model, it will be exactly this, except that there is a sigma n term that takes care of all the different data points. For a single data point, it is exactly this. You are choosing a component, and then choosing the you are sampling the data point given the distribution parameters for that component. Okay. Right. So, before I go into that, this is just, so remember this is another distribution. One use of it, as I just showed, is to model clustered data, but you can also model other kinds of data with it. For example, so let us look at another data set. I got this from the web. So here is the density curve from, so the fitted density curve for some data set which is records precipitation in some falls, I can't pronounce it well also, Snoqualmie Falls. Okay. And so suppose we want to model this density, right, we can model this with a Gaussian mixture, right, and let us see how it looks when we do it with a Gaussian mixture with two components. Right. So, we are trying to model this with a Gaussian mixture. This is one Gaussian and this is another Gaussian. Okay. It does not look like it is modeling this well, but we can increase the number of components, and when we use 9 components, it takes some time, and there you see it is getting closer and closer to this distribution, right. So, a Gaussian mixture with 9 components, of course each of these Gaussians have different means and covariance parameters, is modeling this reasonably well. So, a Gaussian mixture by that way is very versatile. It can model a lot of different distributions by just choosing the right number of components and choosing the parameters appropriately. So, it models not just clustered structure. Yeah.
How do you know what is the right number of components?
Yeah, you do not know. So that's the parameter estimation task, right. When you want to estimate, when you are fitting the model, you want to estimate what the right number of components is, and you want to estimate what these parameters are, right. So if you are just given the data, you do not know what those parameters are, and that is in fact going to be the bulk of the lecture. How are we going to estimate the parameters? All right. So whenever you see this, actually I think I am going to keep this model handy here. So it would be very good if you sort of keep this model in your mind as we go through the lecture, because all the different all the maths that we will see will sort of start making sense when you have this model in your mind, right. So when I talk about some formula like this, the probability of xn being equal to sigma k this probability times this probability, you can see that it is just the probability of xn being generated, and the generative model is usually more easy to think with. So the generative model would be that I choose the component, and then once I choose the component, I choose the corresponding parameters and generate this xn. So these components, if you are doing a clustering task, they are just the cluster labels. So suppose you have 3 clusters and you want the cluster labels, and if you fit a Gaussian mixture model there, these components, the component values 1, 2, 3 would just become the cluster labels in that case. Right. So this would be a probabilistic way of doing clustering. Alright, so the probability of Zn equal to k, probability of Zn, the latent variable or the cluster label taking a particular value, is the prior probability of the data point xn coming from the component k. Okay. Now suppose you're given some data set, right, like the data set we saw from Snoqualmie Falls or something, right. Suppose you're given that data set, and then you're asked to find what is the what is the label Zn for the corresponding data point, right. So what I mean is suppose you have data points here, you have two clusters, and if you knew how it was generated, then the cluster label for all these points would be say 1, and the cluster labels for all these points would be 2, right. But you do not know this, you do not know how the data was generated, right. So once you are given this data, then you have to infer what these parameters are, and you have to infer, given that you are using this model to fit, you have to infer what the Zn value is for each of the data points. So the Zn values for all the data points in one component will have the same value 1, and the Zn values for all the other data points in the other component will have the same the other values Zn equal to 2. Of course, for clustering it can be interchanged, the exact value does not matter, right. So this probability, the posterior probability of the data point xn coming from component k, is so important that it is given a name of its own, it is called the responsibility. I am going to write that down as well, because we will use it again and again and again. Oh, he asked me not to use this. This is the posterior probability of Zn equal to k given the data, right, and it is also called the responsibility. It is the responsibility of component k for xn, right. So till now the way I have described it is that there are these different components, and only one of these components is responsible for giving rise to that data, but that is the generative point of view, right. But if you look at it probabilistically, each of the components is contributing something to that towards the probability of that data point, and that contribution, the weight of that contribution is given by pi k. So your clustering need not always be a hard clustering of this component versus that component. It can be a soft clustering where the cluster label can be probabilistic. So it can be cluster label 1 with probability 0.5, cluster label 2 with probability 0.3, and so on, right. So when you express it as a probability, then you get the option of doing both hard clustering as well as soft clustering. So now you can use Bayes' rule to get this formula for the responsibility. So this is straightforward, and when you substitute for probability of Zn equal to k, which is the prior, you get pi k here, and the probability of xn, given that you know the component, again keep this in mind, given that you know the component, is the probability of xn given theta k, the parameters for that component, right. So let us write this down as well. Okay. So observe that you do not know the responsibility values until you know all the parameters. You need to know all the pi k's and all the theta k's, which in the case of Gaussian is all the mu k's and all the sigma k's for all the k components, and of course you need to know k. to know the responsibilities. Right. So let us see another very interesting picture. When you are generating the data, here this is again from the same book, he is generating 3 different Gaussians, the red, green and blue Gaussians, and of course you do not know how the data was generated. So when you see the data, you see something like this, okay. And then you try to fit 3 Gaussians into a mixture model with 3 Gaussians, 3 component mixture, and what he has done is he has colored the responsibilities, right. So all these guys have been given the responsibility corresponding to component 1 or component red here. These, so the blue component is responsible for all these data points, green component for this, and here you see in the border it is a mixture of green and blue depending on what probability values are assigned, right. So this is one example of soft clustering. So these values, these data points are not assigned completely to either the green cluster or to the blue cluster. And you can see there are mistakes in inference because of course if you do something like a maximum likelihood estimate, these will be most likely from a single Gaussian, right, and these blue points and these red points will not be identified correctly, okay. All right. So now suppose you are given data, you want to fit a Gaussian mixture model to it to either infer the clusters or to just fit the density. For either case you need to estimate the parameters. And what are the parameters? If you have p dimensional data, k components, for each of the Gaussians we need to find out the k mixing coefficients, we need to find out the mean parameters, the mean vectors which are p dimensional, and we need to find out infer the covariance matrices, right. So for now we will assume that we know k, okay, and I will come back to how k is estimated later. Yeah, for now we will just assume, for example, we see data like this and we decide that k is going to be 3. It need not be the case, but yeah. And from this one, from here itself you can see that this is going to get difficult on high dimensional data because the covariance matrices are going to scale quadratically with dimensions. So as the dimensionality of the data increases, your inference task becomes more and more difficult, right. But anyway, we'll not worry about that right now. So how do we estimate these parameters? We will take the standard route of maximum likelihood. The likelihood is just given by this for the case of Gaussian mixture model with k components, okay. This is for all the n data points, and we take the logarithm which will convert this product to a sum here. The problem is it will only convert this to a sum, the inside summation remains. So what you get when you look at the log likelihood would be the summation of n different logarithm terms, where inside each logarithm there is a summation, and this turns out to be this gives us a lot of problems. So if you go by just differentiating this and getting your equating it to 0, the standard route what you probably did for normal distribution, this summation is going to cause problems and you are not going to get a closed form solution, right, because you can't easily differentiate this, and that is one of the main problems for estimating the parameters of a Gaussian mixture. All right. But just to play with the math, let us still do it. Okay. Let us take the derivatives, but we will make one crucial assumption, which is that we know the responsibility terms. Okay. Let us see how it works out. So, we have the log likelihood, and then let us say we want to find out each of these parameters. So, standard maximum likelihood way is you take each one of the parameters, start with mu k, and take the derivative, equate it to 0, and then see what you get by doing some algebra. So, let me just do this. You have right. So, this is the log likelihood, and what we want to do is find the partial derivatives with respect to mu k first. Okay. So, the summation just remains outside, and log of this would just give us the whole thing below, whatever is inside there. And then we differentiate this part. So, yeah, so this, let us write it down. It's these are constants. Sigma k is a constant here with respect to mu k, and then we need the derivative of this. Derivative of an exponential would just be an exponential. Right. And this times so what you get back the entire formula for a Gaussian here, multiplied by the derivative of this complicated term here. Let's change the, I'm just changing the So, what I really want to say here is, when you do this derivation, what you will find here is that this term comes up, and this is the same as the responsibility term. Okay, which is what I have written here, and then the rest of it is just algebra, there is a very nice book called the Matrix Cookbook, where you will find all these derivatives, complex matrix derivatives, and you can see that the derivative of this term x minus mu k inverse times sigma inverse times x minus mu k is nothing but minus 2 times sigma inverse times x minus mu k when and the covariance matrix is symmetric. So you can just substitute that here, you can continue, and what you get is sigma nk, how did I, times what was it, minus 2 times sigma inverse right. So this dou L by dou mu k just gives us this, and when you equate this to 0 you can multiply by sigma k on both sides, and finally it turns out that you will get a very nice form mu k equal to sigma lambda set n k times xn. So what does this mean? The mean that you have inferred is the weighted mean of all the data points, where the weight is the responsibility. Okay. Right. So remember, we do not know the responsibilities. We have assumed that we know this, but the responsibility has all the unknowns inside it. It has pi k, mu k and sigma k, all of which is unknown. We just assumed that we know this and we substituted it and did the math, right, and we got a nice form for mu k. We can do the same math for sigma k. Again, if we differentiate this with respect to sigma k, we have to just use two different matrix derivative formulas, these, and it is very simple. The derivation is very simple. Do you want me to do it? It's fine, right? Okay. And again you get a reasonably nice form for sigma k, provided that you assume that you know the responsibilities, okay, or the kth cluster is given by the weighted mean of all the data points, where the weight is nothing but the responsibility of that cluster towards this data point. Responsibility is the posterior probability of the latent variable given that you have this data. So essentially it's trying to capture what generated that data point, which of the components generated that data point, right. So all this is just so right now we do not really have anything, we do not have the mean parameters right now. We just know that if we knew the responsibilities, which we do not know, we could get a nice form for this, and without this assumption this derivation does not hold, okay. And the same thing with respect to the sigma k values. When we take the derivatives with respect to pi k, we have to be careful. We have to make sure that we use the constraint. Remember, sigma k, the sum of all the sigma k's must be equal to 1. So we can't directly differentiate this, right. You have to use Lagrange multipliers. Is everybody familiar with Lagrange multipliers? Yes, no? Okay, okay. So then you just take a Lagrange multiplier here, take this constraint and do the differentiation, you again get back the responsibilities. So every time you do this derivative, you see the responsibility cropping up, and if we set this to 0, we can get the lambda parameter as minus n, and we get the value of pi k equal to again this proportion. This proportion again is intuitively very clear. What it is saying is pi k, the mixture weight, is a proportion So if you take the sum of all the responsibilities over all data points over all components, it is equal to n, right. And so the kth mixture weight is nothing but the proportion of the responsibilities that are coming from the kth component towards all the data points, and you are taking the proportion that is given by that by those responsibilities with respect to all of it, the sum of it. So let us summarize. What we found is that we have very nice forms for mu k, sigma k and pi k, given that we know the responsibilities, okay, which is the posterior probability of the latent variable coming from that component, coming from the kth component for the nth data point. So can you think of how you can use this to create an algorithm for estimating the Gaussian mixture parameters? Any?
Start with some assumption.
Exactly.
Substitute them back.
Exactly. Yeah. So this is our first guess. We start with some. We initialize all. So I'll denote by curly theta all the parameters, and we start with some guess of the parameters, and then we will compute the log likelihood. We can compute it because we know we have guessed the parameters, and then we will set the responsibilities because we know again all these parameters are guessed, and since given the responsibility we can compute all the parameters again, we will use this to get a new guess, okay, and that way we will iteratively keep refining our guess. Now this looks very ad hoc, but is actually theoretically quite sound, and this is, we will see that why the reason why this is a good thing to do is we will show that this is guaranteed to increase the likelihood at every iteration, and we will see that when we understand why, when we understand how EM works. Okay. So this turns out to be actually an instance of the EM algorithm, which is very intuitive. Okay. So if you so this is an example of exactly that algorithm. We start with some data, the same data set. We start with some guesses for the Gaussians, and iteratively we see that the Gaussians converge to nicely fitting the data. The parameters that you get here will fit the data very well. The only problem is that it usually takes a long time to come to the right parameters.
And you know the k.
Yeah, we know the k. Till now we know the k. So in this whole iterative algorithm we are assuming that we know the k.